more refreshed and with a bit more coffee now, so let's continue. And in the second part, which is shorter than the first one, I just want to go into detail about one particular additional connection between submodularity and convexity and show you sort of what other algorithmic implications it has. And I'll do this at the example of decomposable functions, but I'll sort of on the way also explain what is the min-norm problem. So yeah, we saw that we can write many interesting problems as subset selection problems. So now what we'll care about is minimizing a set function which is submodular. So remember that picture, and in fact that picture seems to be the most memorable slide of my talk, as I heard from a student who said, yeah, they talked about McDonald's in that class. So yeah, so let me show you two examples where this is actually particularly relevant to solve this, be able to solve this for more than 10 elements maybe. So one is this varsity problem, where essentially the subset selection problem is at the level of I'm selecting which entries in this vector should be non-zero. And the way you usually set this up is sort of you have some kind of loss function plus a penalty term, and the penalty term will penalize the number of non-zeros in this. So this could be the L1 norm or the cardinality essentially of that set. And to make this tractable, one way to do this is to relax this to the L1 norm. Now, if I have more knowledge about what certain special patterns are that I'm looking for, so maybe I'm looking for patterns that I know have to be consecutive or that correspond to certain subtree structures or something like that, I could put this in my penalty. So I could actually, instead of just taking the cardinality, I could in fact put any submodular function there on the set of entries here, which is the support of the vector. But of course then L1 norm is not the correct relaxation, so sort of the analogous relaxation to this would be a norm which is based on the Lovász extension. So now you know what is the Lovász extension. Essentially the Lovász extension gives you a norm. It's a convex function, and you can essentially get a structured norm out of that Lovász extension. And now if you want to minimize this problem, essentially as a subroutine you'll need to solve a submodular minimization problem. And defend that problem that I'll be talking about. So the second example is has many applications in computer vision, but it shows up in other cases as well. If you want to have, for example, a random field and you want to model spatial coherence. So this can be viewed as just if you have, say, two labels for simplicity, distribution over binary vectors. Or of labels of between 0 and 1, and as we know that is the same as subsets. So binary vectors and subsets are equivalent. So you could see this as a distribution over sets, the set of points that have label 1, variables that have label 1. So now I get this distribution. This distribution, if this is defined by a submodular function, this is the case if, for example, I have something like positive correlation or spatial coherence or temporal coherence that I want to model. Now I may be interested in finding the assignment, the label assignment that has the highest probability, so that means maximizing the probability or minimizing this f function. If it's submodular, it's going to be just a submodular minimization problem. There may be other problems that I'm interested in computing, for example, marginal probabilities of certain labels being 0 or 1 and things like the partition function of the z function down there in this also. And it turns out these can be approximated also by solving a submodular optimization problem. So in fact, the min-norm vector will give you sort of this closely connected to these approximal marginals. So these are two motivating applications. So we want to solve this at scale, and as you saw from the previous slides, sort of the fully polynomial time algorithms with the n to the 5, etc., or even n cube does not really look like solving it at scale. So that's going to be a bit more tricky, but in many cases what we have is actually that the submodular function in practice has a lot more structure than just being a submodular function. So in many cases what we have is that my submodular function is actually a sum of functions. For example, a sum of potential functions, or a sum of hypograph edges, or a sum of cut functions where the cut is now in a simpler graph, or something like a concave function of a cardinality, which can also, all of these can be solved essentially in linear time by themselves, much more easily. So we would like to use that, but of course if I take a sum of these and each of these has sort of their own subroutine, that subroutine won't work for the sum of them. But we'd like to still exploit that, so let me show you how you can exploit this potentially. So we want to use the fast subroutine. So now what we'll assume is that we can solve f plus some linear function. Linear function usually is pretty easy to handle in these cases. And we have a specialized subroutine for solving this, but not for the sum.
So when you say linear function, it means like there's a weight for every element?
Yeah, every element has a weight, so sum of weights, essentially. Yes. So people have looked at this, and there's essentially two ways of addressing this problem. One is via combinatorial algorithms that again go sort of via the specific non-smooth dual. The other one is using convex relaxations. So going via the Lovász extension and solving the convex problem and using convex optimization methods. So I'll go now into detail of the second one. So we can do the same spiel that we did before. So we have our discrete set function, and now we relax the problem. So we use this Lovász extension. We just saw the Lovász extension is useful. So now we could just use the Lovász extension of a sum of functions. And we know this is exact. So the Lovász extension of the sum of function is the sum of the Lovász extensions. That's easy. I can compute that, and now what I have is I have a minimization of a sum of convex functions. So if you know a little bit about convex optimization, minimizing a sum of convex function, this is a problem that's very well studied in the literature. So like there's methods for addressing this, and these are called dual decomposition methods. And in fact, since this is a non-smooth problem, there's also ways of smoothing it. Smoothing only works if you have a simple function for reasons I can explain if you're interested in later after the talk. So you can do decomposition methods like this, and people have tried this, and it kind of works. It essentially enables you to solve each of these only ever by itself. But again, what we have sort of this non-smooth function. So convex optimization with a non-smooth function is sort of the slowest one you can often get. So it turns out there's another relaxation that you can use, and instead of exactly this one, with a slight perturbation. So now I take my relaxation, I remove the constraint that I'm in 0, 1, and instead what I'm adding is some convex function. Some smooth, strongly convex function. Or actually strictly convex is enough. So this convex separable function now, it makes the problem sort of more curved. And now I could solve this problem. Or what I could solve is the dual version of this problem. So the convex dual of this problem has the following form. Now the convex dual is an optimization problem over the base polytope, and the optimization problem has a simple objective. It's just a squared norm. So what this says is that find me the point in that base polytope that has the smallest norm, or the point that is closest to 0. So in pictures here is 0, so the point that is closest to 0, that's the point that I'm looking for. Now this is a smooth optimization problem. It's also called the minimum norm point problem. And this is known to be another way of solving the submodular minimization problem. And in practice, this performs usually much better than the subgradient methods. So, okay, so you see you get sort of the smooth problem out, but the question is, why does this actually work? So obviously, the solution to this problem and the solution to this problem are not going to be the same. And in fact, I could even scale this up, so certainly these are not going to have the same optimal solutions, unless like my perturbation is very, very tiny. And it turns out it doesn't matter. So the only thing that I really will care about is which entries of this guys are positive and which are negative, and the positive ones will be the same that are sort of bigger than 0 in this guy. And that's all I care about. But let me show you a bit more of the details of why this actually works. So what we get out is 3 different optimization problems. The first one is, well, the proximal problem. We call it the proximal problem also. And it's convex dual. So the relation between this is just convex duality, and it turns out if you can solve one, you get the solution, optimal solution for the other pretty easily by flipping the sign. So that's pretty easy. So this one is the geometric projection problem. This one is the proximal problem. Now how does this relate to my discrete function? So here's the relation. It turns out that the proximal problem gives you a solution of a parametric submodular optimization problem. So here f of s is my submodular function, and what I do is I penalize the cardinality of my set. So obviously as alpha goes to infinity, the solution of this thing will be the empty set. I penalize everything. I'm going to try to make it as small as possible. I'm going to take nothing. If alpha goes to minus infinity, this term will dominate, and I'm going to take everything. And in between, I'm going to get something that's between everything and nothing, so I'll get some solutions that are not the empty set and not the full set. And in particular, if alpha equals 0, I'll be back at the solution that I was actually looking for. So this problem has sort of a sequence of solutions. I can do this for any discrete optimization problem. The nice thing about submodular functions is that the sequence of optimal solutions here forms a nested set. So that's not always necessarily the case, but if I have a submodular function, what these look like is sort of, I get everything, and then I sort of get a smaller set and a smaller set, and these are all subsets of each other, and in the end I get nothing. So since these are subsets of each other, I can encode all of them in one vector by essentially saying that if I take this vector and I threshold it at a certain alpha, this is going to give me the optimal solution of that problem for that particular alpha. So here, if I threshold at 1, I'll get only this one. If I threshold at 0.5, I'll get this one, and so on. So essentially, I can encode all of these in one vector, and that's going to be the optimal solution to that proximal problem. So this needs to be proved, but I'm just claiming this is the case. And vice versa, if I can compute submodular function optimization fast, there's a way of sort of smartly using that to get from the parametric solutions to the proximal problem by a divide and conquer method. So you can go either way. So these are equivalent. So what we gain from this is now 3 different optimization problems, and if we can solve one, we can solve the other 2. And this is going to be nice. So first of all, what this shows is that we can solve any of these convex problems to get the optimal solution for our problem by taking the alpha equals 0 solution, so threshold at 0. The second thing is, we get the exact relaxation. The second thing is that we actually also go the other way around. If we know how to solve any of these efficiently, we know how to find do a projection onto our base polytope. So to find, if I get any point, find its closest point on the base polytope. And it turns out that's not much different from this problem. Essentially, it's a small change of that problem. If I can do one of these, I can solve my submodular optimization, and I can project onto the base polytope. So find the closest point on the base polytope by solving that combinatorial problem. So this is what we are going to use as a subroutine, so keep this in mind, this analogy that we can do all of these now for my little FIs. For each single FI, I can solve all of these. So now let's go back to our sum of submodular functions. So what does this now become? So I have my sum of submodular functions. I take the Lovász extension and I smooth it out. And now I look like at the dual problem, so that's sort of the analogy of the min norm problem. So the dual problem is a very geometric problem. So let me first show this in pictures. Essentially, it's going to be the problem of having 2 convex sets, and I'm trying to find the 2 closest points between those convex sets. That's what I'm trying to do here. I minimize y and lambda to find the points that are closest. Now my constraint on y now is a vector, stacked vector of little vectors yi. I have one vector now for each of the fi's. So that's my decomposition. And I have one variable lambda, one big vector lambda, that sort of will be the agreement variable. They have to sum up to 0. So lambda, it has the same size as y. And y now is the stacked vector. So what this also means is that y is a vector that lives in a product of base polytopes. So it's like each of these little ones lives in one of the base polytopes. So hence I have the product down here. Okay, so this is now my dual problem. So now I'll try to solve this dual problem. This is a very geometric problem. And it's also, this type of problem is called a best approximation problem. And it's sort of a generalization of the problem. Try to find a point at the intersection of 2 convex sets, for which we have very classical methods available. So how could I solve this problem? And the maybe simplest thing is do an alternating minimization. So what does alternating minimization become in this problem? Let's say we start out with some arbitrary feasible solution set. Y lives in the blue set and lambda lives in the green set. So I keep lambda fixed and I update y, so that means I find the closest y to lambda, so I project lambda onto the blue thing, onto my base polytope, so I find the closest point on this side. And now I fix y and I update lambda, I find the closest point on the right hand side, and so on and so forth. And this is an alternating projections algorithm that it becomes, and it's guaranteed to find the optimal solution. So it's a convex optimization problem, so it's going to be, I'll show you the convergence rate. So you know sort of within that many steps, you'll get an error of like within close to epsilon, and then you know like how many steps you need for error of to epsilon. So the thing is, this thing is actually, it's not fully polynomial time, but it's going to be log of 1 over epsilon times something. Yeah. So it's going to converge linearly. Okay, so the question is, how do we actually solve these projection steps? That's essentially what we have to solve in this algorithm. If we can do that, we can solve it. And now what I told you about the projection oracles that we have, that's exactly where it comes into play, that we know for each fi we can project onto the base polytope. But now if we find the closest y vector, we have to only sort of find the closest yi and b of fi. So these projection problems I can solve in parallel. If I have r functions, I have r projection problems, I can solve these. And the other direction is easy because it's just an averaging. So I can solve this. I have this algorithm now, I can implement it, I can run it. Now this is actually only one algorithm in like a collection of algorithms that where I could use this simple fast subroutine of projecting onto the base polytope fast. And I want to show you another version that works actually better in practice even. So there's other methods you can do. I don't want to go through all of them. Let me give you the intuition of using reflections instead of projections. So for simplicity, that's where these methods come from. Let's assume we want to just find a point at the intersection of two convex sets. So I have just like two subspaces, I want to find an intersection. If I do alternating projection, it's gonna like wiggle and wiggle and wiggle. It sort of get epsilon close, but it's gonna take essentially infinitely many steps to really like exactly get there. What I can do instead here is the following, that instead of doing a projection, I do an over projection. So don't look at the formulas, look at the pictures. Essentially what I do is instead of going here, I take double the step, and then I take double the step into the green area, and then I average with my previous point. So these are called reflections because it's like, think of it as a mirror, you're sort of going the other way around. And if I do this and I take my iterate to be the average between these reflected points and my previous points, I converge in 4 iterations. It takes a curve, so the path is different, but it converges very much more quickly. So this may be an interesting option, but the question is, now we have sets that don't intersect and we have these polytopes and not something simple like that. So what does it look like in our case? So we have our base polytopes and just the subspace line. So alternating projections, as I claimed, is going to converge. It's sort of like slowly walk there. If I do reflections, I'll do these reflections, take the average. So what happens is actually that my iterates actually go off to infinity. Yes. If the sets don't intersect, this is not going to converge. But what does converge is that if I take now my iterates and I project them back onto my polytope, that's going to converge. And you see that actually this converges faster here also than my left-hand side. And this is always going to be the case if you have two convex sets and they don't intersect and you run this reflections thing, it's going to diverge, but what will converge to your optimal solution is the projected version of the diverged sequence. So what does this look like empirically? So here's just the plot. These are algorithms, it doesn't really matter what exactly they are. These are algorithms that solve this problem. These are algorithms that solve just the minimize just the non-smooth Lovász extension. So here on the x-axis I have number of iterations, on the y-axis I have the duality gap. And these methods tend to converge much, much more quickly than those ones. In the discrete version of the problem and in the continuous version of the problem. So these methods actually help in terms of number of iterations, and now 1 iterations in each of these methods, if I do decomposition with one or the other, is essentially the same complexity. So this does actually help empirically. The question is, can we say anything theoretically about this? So the question about, like, if I take now, like, say, t steps, how far am I from the optimum? And I'm just want to show you, give you sort of an intuition how you would analyze this for the alternating projections method. So here's the theorem. What you can show is that both y and lambda will go to the optimal solution, like the actual optimal point at a linear rate, and hence also the function values are going to converge to the optimal value at a linear rate. Not only the relaxation, but also the discrete actually. So now what I'm actually interested in is this discrete problem, right? So I'll solve this one up to a certain accuracy and then I round it, and I want that my discrete vector that I get out of it is not too far from the optimal solution either. So I get convergence also in the actual discrete problem. So So what does linear convergence mean? Essentially it means that if you take t steps, your error will shrink by a factor alpha to the t, and now alpha is something smaller than 1. So it's going to shrink. So what you'll essentially need is like 1 over epsilon, log of 1 over epsilon many iterations. So how would you show such a thing? Let me just give you an intuition again from subspaces. What does the convergence rate of this thing depend on? If I just want to find a point in the intersection of these two lines, I'm going to iterate and iterate. It depends essentially for different angles of the lines, it's going to be converging at different speeds. So essentially what it depends on is the angle between these two lines. The smaller the angle, the longer it'll take to converge by this picture. And in fact, the convergence rate here is exactly the cosine of the angle of these things. So the alpha that sort of by which it shrinks, that's exactly the cosine of the angle. So that's the proof for the like subspace case. That's very well known. Now in our case we are slightly different because we have two sets that don't intersect, and these sets are polyhedra instead of lines. But the intuition is essentially the same. So if you analyze this, essentially what you'll have to do is you can relate the convergence rate again to some notion of angle between subspaces. And now the problem is now you have lots of angles because you have this edgy thing, so you have this edgy polytope. Essentially you have lots of different possible angles, and you essentially have to bound the worst one of all of these possible angles. And that's going to be the sort of this polytope is going to be my base polytopes, and that's sort of
the exponential element, right?
Angles, yes,
yeah.
yes. So yeah, because you have exponentially many faces. Yes, and also you have actually have the product of our base polytopes, so sort of you have even like the combination, like for each of those you have a different face essentially. You have to bound all of those. And then once you have done that, you have the convergence rate for the continuous version of the problem, then you have to relate it to the discrete version. So I don't want to go through all of this. I want to show you sort of an intuition how you would give a bound on sort of the angle of all possible of these angles, exponentially many, plus it's actually a product of polytopes. So for each polytope you have one of these faces active essentially. So how would you do this? Essentially you start out with 2. Let's just pick an arbitrary face and let's pick my subspace. Like sort of the angle between those, what we'll measure is the cosine of the angle between those, and then we'll take sort of the maximum cosine over all possible combinations here, so over all these possible guys. So this thing is called the Friedreichs angle. It's essentially just a generalization of an angle. If you think about what's the cosine of an angle between two vectors, it's the dot product, essentially normalized dot product. So this thing is going to be sort of what's the largest dot product you can form between vectors of these two different sets. And then sort of being orthogonal to the intersection, that doesn't count. So that's essentially what this Friedreichs angle is. So how do you get the Friedreichs angle now? Let's start with 2. Let's fix one of these faces and let's fix this one. What you do essentially is you express this face by a matrix. That's the constraint matrix for that particular face, and that's going to be the null space of this matrix. And then the cosine of the angle is the largest eigenvalue of the product of these matrices Tp and T lambda. So it's the largest singular value of Tp T lambda, or the largest eigenvalue essentially of the A transpose A thing. So let's call this M. Now we want the largest eigenvalue of this thing that is strictly smaller than 1. So how do we bound that eigenvalue? Now the thing is, now the submodularity comes in, because now we have to use some properties of what does Tp look like. T lambda is pretty simple. This is just this averaging thing. So how do we do that? And we have to now go back to our base polytope. So the face that we'll have is actually going to be some of these faces or some of these lines in 2D of that base polytope. So what's the base polytope? It's defined by some constraints, and at this edge sort of, some of these constraints are going to be tight. That means some of these are going to be satisfied with equality. So I have some sets whose inequality is going to be an equality at each boundary, essentially. So I'm going to collect these sets, and what it turns out to be that these actually again form a nested set. So somehow we always get these nice nested sets. From these nested sets, as you see, define a partition of my ground set. Because the dimensionality again is sort of the number of elements. We again view all of these as weight vectors. So we have this thing, and this thing is going to help us. So this is a representation now. For each particular face, I get one of these partitions. And now I'll just have one partition for each of these R different base polytopes. And now essentially the eigenvalue depend on how these interact. So let me just show you this as a picture. So if y1 lives in bf1, and if it's on one face, I'm going to get one partition for f1 and the base polytope of f1, one partition for y2 and the base polytope of y2, and all of these different ones. And now what I'll have to look at is what's the relation between those. So to do this, what I'll do is I'll take these partitions, and each parts I'm going to make it a super node. And I'm going to look what's sort of like, where does this guy have a similar same element as this one? That's where they intersect essentially. Cross intersection, and I'm going to make a graph where I connect the ones that share an element. So these are just the ground sets with the same 1, 2, 3, etc. elements. So if they share an element, I'll connect these different nodes. So I can do this for all possible ones. I just did it only for one, for two as a picture. And now the matrix that I'm interested in is going to be the weighted adjacency matrix of this. And now to get now what we want is we want to bound the eigenvalue of that particular weighted adjacency matrix of this very regular R-partite graph. We'll get this by bounding the eigenvalue of the Laplacian of that graph. And to bound the eigenvalue of the Laplacian, there's some very nice spectral graph theory. Essentially, we can use Cheeger's inequality. What Cheeger's inequality says it relates cuts in the graph, normalized cuts essentially, to eigenvalues of the Laplacian. And it turns out that particular eigenvalue that it involves is exactly the eigenvalue that we're interested in. So we look at this graph, and looking at the graph, sort of bounding the worst case cut is much easier than looking at a matrix and figuring out, or looking at these different angles, like what's going to be the worst possible of these faces. So that's much more easy to look at. So we can essentially, by looking and by analyzing this graph, get the worst cut. The worst cut is going to correspond to the worst partition of the faces essentially. So like I'll have different kinds of partitions now. And that's going to give me now the eigenvalue, and that's going to give me the convergence rate. So that's how the proof sort of brings in some other elements, but we can do it essentially, get the exact bound, because we have this nice structure of the base polytope and submodularity. So we get a sort of faster algorithm, and we get an easier way of analyzing it because we know the properties of the base polytope. Okay, with that, let me just wrap up. So what I showed you in the second part is how you can actually, using the analogy between submodularity and convexity and this additional relaxation, write the discrete submodular minimization problem as this geometric best approximation problem, which gives you a new set of new algorithms that you could use. And you get linear convergence rates out. It has some special cases. So what I showed you is sort of the most generic case of the convergence rate. You can get this convergence rate better for certain special cases of this function. This algorithm has actually been used for inference in this paper, so they have a tighter bound. It's still an open question, like what are other cases? So you observe empirically that this algorithm works very well for certain cases, but I don't have like a good theory of like other special cases that would improve your convergence rate to something better than it is currently. In the worst case, this is sort of the best you can do. The second thing is that now what I showed you is sort of the bound for these alternating projections. It turns out the same kind, what essentially it says is a certain kind of growth condition, like if I take so many steps, I definitely decrease the objective by so much. This same kind of condition can be used also to analyze other kinds of algorithms like stochastic gradient and block coordinate descent methods. With the same, building sort of on the same kind of proof and rates that you get out here. So it's still open, like is there other algorithms where you can use that same kind of technology. So with that, thanks a lot for your patience in listening to me, and I hope you learned something, and let me know if you have any other questions. I'm here to discuss. Okay.
Yeah. So just I guess we press for sure. Quick question.
Yes.
So the thing you showed seems like you're I don't know if you're analyzing an MCMC algorithm, right? You're not analyzing an MCMC algorithm, right? You're not bounding a mixing time.
Yes, but I mean it's...
The technology you went through seems to imply that you're bounding a mixing time.
Well, because if you look at mixing time, essentially it's a Markov chain, right? And the convergence of the Markov chain depends on the eigenvalue. It depends also on the Fiedler value of essentially the second eigenvalue of the graph.
Right.
So it's the same kind of eigenvalue that depend on, yes.
Right. So I'm saying
Yes.
is there a Markov chain, an MCMC algorithm that is equivalent to your algorithm? Or
I think the difference is that I'm not exactly sure. So I actually thought about this, and I cannot say exactly for sure that there is. So the thing is, if you look at like Markov chain, essentially all of these are fixed point methods, right? So it's going to be like you're multiplying a matrix with your vector over and over again. So for the Markov chain, that's going to be the thing in expectation. That's how sort of the thing evolves in expectation. Expectation will converge to your distribution. Now in this thing, that's exactly your vector, and I'm not exactly sure that this can be sort of directly mapped to a probability distribution too easily. But the intuition, it's the same thing. It's a fixed point method, and sort of the convergence rate will depend on these eigenvalues. So that kind of part is exactly the same. Whether you can find exactly a Markov chain that does exactly that same exactly that thing between base polytopes, maybe there's a way. I don't exactly know, because now it's not exactly an expectation, so these matrices. So yeah, but that's
I understand your algorithm is not.
Yeah, but the sort of the higher level bit is that yes, all of these in the end are these fixed point methods, so all of these have sort of the same kind of properties because of that. Yeah.
Okay, let's thank the speaker.